Welcome to today's paper reading. Today's paper is titled, Controllable Text Generation for Large Language Models, a Survey. This paper, published in the ACM Journal, surveys the advancements in controllable text generation for large language models by Liang and colleagues from Renmin University of China and the Institute for Advanced Algorithms Research. The introduction of the paper focuses on the objectives of controllable text generation, CTG. CTG aims to ensure that generated text adheres to predefined control conditions while maintaining high standards of text quality. Control conditions can be explicit, such as following a specific writing style, or implicit, like ensuring the text is non-toxic. Additionally, CTG emphasizes maintaining text fluency, helpfulness, and diversity to enhance the applicability and effectiveness of the generated text. Figure 1 showcases the increasing number of publications related to control generation in language models as indexed by Web of Science. This growth reflects the expanding interest and demand for controllable text generation, CTG, research, highlighting the need for LLMs to generate content that meets specific requirements while maintaining high-quality standards. Figure 2 illustrates the dual dimensions of large language models, LLMs, in controllable text generation, CTG. The first dimension, controllability, focuses on how the information is expressed, such as sentiment and style control. For instance, in sentiment control, the model ensures the emotional tone aligns with the intended sentiment, whether positive, negative, or neutral. The second dimension, capability, highlights the objective knowledge capabilities of LLMs, like logical reasoning and problem solving. Importantly, CTG does not imply that positive sentiment is inherently better than neutral. It adapts to various application scenarios and requirements to achieve the most suitable generation outcome. Figure 3 presents the comprehensive framework for surveys in controllable text generation, CTG. The framework categorizes CTG tasks into content control, hard control, and attribute control, soft control, highlighting the distinction between specific linguistic elements and abstract semantic attributes. It also outlines the two main stages of CTG methods, training stage methods, which include retraining and fine-tuning, and inference stage methods, such as prompt engineering and latent space manipulation. Additionally, the framework emphasizes the importance of evaluation standards, distinguishing between general metrics and task-specific metrics to assess the effectiveness of CTG methods. Table 1 provides a comprehensive summary of key surveys in the field of controllable text generation, CTG. It categorizes the surveys based on various dimensions such as models, including PLMs and LLMs, tasks, abstract and concrete attribute control, and learning-based methods, training, fine-tuning, and reinforcement learning. Additionally, it covers unlearning methods, evaluation methods, and application scenarios, highlighting the scope and depth of CTG research. The table also discusses control mechanisms, quality considerations, challenges, and future research directions, ensuring that the latest developments in CTG are covered. The fundamental principles of text generation in large language models, LLMs, are based on the transformer architecture. These models generate text by computing the conditional probability of sequence elements, ensuring each new token logically aligns with the preceding context. In controllable text generation, CTG, the objective is to integrate control conditions into the generation process while maintaining text quality. These conditions guide the model to produce text with specific attributes. The problem of CTG can be represented within an ideal semantic space, a multidimensional vector space where semantic vectors can be manipulated to align with desired attributes without compromising other semantic qualities. In the realm of controllable text generation, there are three primary tasks: content control, attribute control, and topic control. Content control, also known as linguistic or hard control, focuses on specific elements like structure, vocabulary, and length. This ensures the text adheres to predefined rules and formats. Attribute control, or semantic or soft control, deals with abstract attributes such as sentiment, style, and safety. This type of control influences the overall characteristics of the text without strictly defining linguistic expressions. Topic control ensures thematic consistency and compliance with legal requirements, as well as personal style adaptation. These tasks collectively contribute to the broader research area of controllable text generation. In the training stage of controllable text generation, several methods are employed. Retraining involves training models from scratch using specialized datasets, often necessary when pre-trained models are inadequate. Fine-tuning adjusts pre-trained models by incorporating control attributes into the model's parameters, offering an efficient approach with less data and computational resources. Reinforcement learning uses reward signals to guide model outputs towards specific objectives, suitable for complex tasks like maintaining a specific style or sentiment. During the inference stage, interventions are applied in real time. Prompt engineering guides the model's output by manipulating input prompts, using either hard or soft prompts. Latent space manipulation controls the generated text by adjusting activation states within the model's hidden layers, allowing for precise control without altering model weights. Decoding time intervention modifies the probability distribution of the generated output or applies specific rules during decoding, ensuring alignment with control conditions. Various control methods include attribute control, content control, and adapter-based approaches, each with specific representative methods. Figure 4 illustrates the process of injecting conditions into controllable text generation, CTG. The figure categorizes CTG methods based on the stage of model intervention, distinguishing between model-driven and data-driven approaches. Model-driven methods utilize classifiers, conditional language models, and knowledge injection directly from the LLMs themselves. In contrast, data-driven methods leverage external data resources such as text corpora, lexicons, graphs, and databases to inject knowledge. The figure highlights the dual stages of CTG methods, the training stage and the inference stage, each with its unique methodologies and applications. Figure 5 categorizes controllable text generation, CTG, methods into two main stages, training and inference. During the training stage, methods like retraining, fine-tuning, and reinforcement learning are employed to incorporate control attributes into the model. In the inference stage, techniques such as prompt engineering, latent space manipulation, and decoding time intervention are used to influence text generation in real time. This classification helps in understanding the various approaches to achieving controllable text generation. Table 2 categorizes the stages and methods of intervention in controllable text generation, CTG. It highlights the training stage with methods like retraining, fine-tuning, and reinforcement learning, and the inference stage with methods such as prompt engineering, latent space manipulation, and decoding time intervention. Each method is further detailed with specific examples, providing a comprehensive overview of how different techniques are applied in CTG. The training stage methods for controllable text generation primarily include retraining, fine-tuning, and reinforcement learning. Retraining involves either constructing a new model from scratch or fundamentally modifying an existing model's architecture to better accommodate specific control conditions. This approach ensures that the model intrinsically adapts at both the architectural and parameter levels. Fine-tuning, on the other hand, adjusts a pre-trained model using a smaller, specific dataset to better align with particular control attributes without the need to train the model from scratch. This method involves minor adjustments to the model structure and updates to the data, refining the model's output for specific tasks. Reinforcement learning optimizes text generation by iteratively improving the model based on feedback or reward signals. These signals indicate how well the generated text aligns with specific goals, dynamically adjusting the generation process based on complex evaluation criteria. Figure 6 illustrates the implementation of control codes in the control model. These control codes are prepended to the training text and encapsulate specific requirements related to domains, styles, and themes. The control model learns the distribution P, X, C by conditioning on these control codes, which provide a control point in the generation process. This approach establishes a connection between the text and specific attributes through the natural co-occurrence of control codes and the text. Figure 7 illustrates the issue of spurious correlations in text generation, where the model mistakenly identifies irrelevant features as significant attributes. This can lead the model to rely on unintended aspects of the input, rather than the intended control codes, thereby degrading the quality and controllability of the generated text. To address this, FAST introduces the Importance Policy Sampling (IPS) method for data resampling, which generates counterfactual examples and uses a feedback mechanism to enhance the model's performance. Table 3 provides a summary of the various research directions and fine-tuning (FT) for controllable text generation (CTG). The table categorizes these directions into adapter-based fine-tuning, data-driven fine-tuning, and multi-attribute generation. Under adapter-based fine-tuning, methods like auxiliary tuning, disc-up, and li-fi are highlighted. Data-driven fine-tuning includes notable approaches such as FLAN, instruct-CTG, and REI. For multi-attribute generation, the table mentions DCG and CLMI as key methods. Each category is designed to enhance the model's ability to generate controlled text through different mechanisms, whether by adding components to the model, using specific data forms, or controlling multiple attributes simultaneously. Figure 8 illustrates the relationship between controllability and helpfulness in controllable text generation (CTG) tasks. It categorizes responses into 4 quadrants based on their alignment with these 2 attributes. The figure highlights how different prompts can yield varying levels of controllability and helpfulness. For instance, a prompt asking for quick weight loss advice can result in responses ranging from normal CTG to bad LLM outputs. Safe RLHF is introduced as a method to dynamically balance safety and helpfulness by handling human feedback separately for each attribute, ensuring generated content is both useful and harmless. In the inference phase, several methods are employed to control text generation. Prompt engineering uses both hard and soft prompts to guide the model without altering its parameters. Hard prompts are discrete and expressed in natural language, while soft prompts are continuous and trainable vectors. This method facilitates efficient few-shot learning. Latent space manipulation involves adding guiding vectors to the model's activations to direct text generation without retraining. This method allows for precise control over the generated text's characteristics. Decoding time intervention manipulates the model's output probabilities during the decoding process to steer the text towards desired attributes. This technique enables dynamic control over the generation process and ensures the output aligns with specified requirements. Figure 9 illustrates the difference between hard and soft prompt methods in controlling text generation by large language models. Hard prompts use explicit natural language text to guide model generation, typically relying on predefined trigger words or text prompts. Soft prompts, on the other hand, use continuous, trainable vector embeddings, offering more flexible and fine-grained control without altering the underlying model parameters. Both methods aim to guide the model in generating the desired text by providing clear instructions or examples, achieving efficient few-shot learning in resource-limited scenarios. Table 4 provides a detailed comparison of various prefix-based tuning methods used in soft prompting. These methods include prompt tuning, prefix tuning, and p-tuning, each with distinct optimization scopes and methods. Prompt tuning directly optimizes prompt embeddings, prefix tuning uses FFN to optimize prefix parameters, and p-tuning employs an LSTM-based prompt encoder. These methods are designed to enhance task performance without modifying the underlying model parameters, offering flexibility and efficiency in controlling the generation process of language models. Table 5 provides a comprehensive summary of the various research directions in decoding time intervention for large language models. It categorizes these interventions into 4 main areas: classifier guidance, intervention method innovation, special issue resolution, and scoring function innovation. Each category lists specific methods and their corresponding research papers, offering a detailed overview of how these techniques manipulate the logits or probability distribution of the model's output to steer the generated text towards desired features or control attributes. This table is crucial for understanding the current state of research in controlling text generation at the decoding stage. Figure 10 compares PPLM and Fudge and their approaches to controlling text attributes during generation. PPLM uses backpropagation to adjust hidden states, while Fudge directly modifies logits to align with expected attributes. Both methods employ external classifiers to guide the generation process, ensuring the output meets specific control conditions. Figure 11 compares three different methods for controlling text generation in large language models: GUDE, DEXperts, and PRED. GUDE employs Bayes' rule during decoding by combining the outputs of a base language model and a class-conditioned language model to calculate the probability of generating the next token. DEXperts offers a straightforward contrastive decoding approach by modifying a pre-trained language model's predictions using expert and anti-expert models. PRED controls text generation attributes by comparing and adjusting the logits generated by different prompts, using a prefix-adaptive decoding method to influence the output intensity. The evaluation of controllable text generation (CTG) tasks can be categorized into three main types: automatic evaluation, human evaluation, and LLM-based evaluation methods. Automatic evaluation uses metrics like Bilu, Rouge, and Meteor to assess overall text quality and task-specific attributes. Human evaluation provides a more nuanced assessment through metrics such as fluency, coherence, and topicality, using methods like A/B testing and Likert scales. LLM-based evaluation leverages powerful language models to offer diverse and practical evaluation, reducing costs and subjective biases. Benchmarks like CTRL-Eval and ConGenBench further standardize the assessment of generation models. Table 6 provides a comprehensive summary of various evaluation methods and metrics used in the context of controllable text generation, CTG. The table categorizes these methods into three main types: automatic evaluation, human evaluation, and LLM-based evaluation methods. Under automatic evaluation, it further divides metrics into general and task-specific evaluations. General metrics include n-gram overlap-based metrics like Bilu, Rouge, and Meteor, which assess the similarity between generated and reference texts. Language model-based metrics such as perplexity, BERT score, and mover score evaluate text quality by considering semantic information. Distance-based metrics like TR, CIDR, and SPICE measure the quality of generated text by comparing it with reference text using various techniques. Task-specific metrics often involve using classifiers to ensure the generated text meets specified attributes. The table also briefly mentions human evaluation methods and LLM-based evaluation approaches, highlighting the diverse range of tools available for assessing CTG performance. Table 7 provides a summary of commonly used base models and datasets for training classifiers and various attributes such as emotion, topic, and toxicity. For emotion classification, models like BERT, Roberta, DeBarta, Distilbert, and MacBERT are utilized with datasets including IMDb, Amazon 5, Yelp, Twitter Sentiment, and Daily Dialogue. Topic classification employs BERT and Roberta models with datasets such as AG News and Dpedia. Toxicity classification uses Roberta and DeBarta models with datasets like Jigsaw Toxic Comment Classification Challenge and Real Toxicity Prompts. CTG technology has developed diverse control generation methods to meet various generation needs across different fields. These methods can be categorized into vertical domain applications and general task applications. Vertical domain applications are tailored to specific tasks within particular industries, focusing on specialization and precision. For example, in news generation, Deep Press integrates pre-trained models to produce topic-aware news content, enhancing objectivity and coherence. General task applications address cross-domain needs, offering high versatility. For instance, in toxicity control, SRDT manipulates attention layers to reduce toxic content. Additionally, CTG technology also enhances niche applications like recipe generation, where Recipe with Plans combines content planning with sequence generation to produce coherent and logically structured recipes. The challenges in text generation by large language models, LLMs, include issues of incoherence and semantic ambiguity, especially in complex tasks requiring precise responses. Additionally, the large parameter sizes of current LLMs often result in time-consuming text generation, affecting real-time applications. Controlling multiple attributes simultaneously, such as emotion, style, and topic, remains a significant challenge due to complex interdependencies. The research appeals emphasize the need for more practical applications, expanding the diversity of testing tasks to include linguistic style and narrative structure, and maximizing the capabilities of LLMs when comparing baselines to ensure the chosen methods are representative and practical. This paper concludes by reviewing the latest advancements in controllable text generation, CTG, for large language models, LLMs. It systematically defines basic concepts and introduces a new task classification approach, categorizing CTG tasks into content control and attribute control. Key methods during training include retraining or fine-tuning pre-trained models and employing reinforcement learning strategies. During inference, techniques such as prompt engineering and manipulating the latent space are commonly used. The paper also explores evaluation methods and highlights the wide application of CTG technology. It discusses challenges like improving quality and control precision, and proposes future research directions. Thank you for watching.